Hey there, this is our related rates day 2, 2.12 notes. Go ahead and try the warm-up, pause the video, and when you are ready, we will go over the warm-up, which is just some basic derivatives for you. All right, so number 1, we have the derivative of tangent of 2x. This is the chain rule, so we want to start by doing just the derivative of tangent, which is secant squared. And we're going to leave our 2x untouched. Then we're going to multiply by the derivative of the 2x, which is 2. Number 2, chain rule again. So we have the derivative of e to the 4x, which is e to the 4x, times the derivative of 4x, which is 4. Okay, number 3, we want to think of this as x squared minus 1 to the 1/2. This is chain rule again. So we have 1/2 x squared minus 1 to the negative 1/2 times the derivative of the inside, which is 2x. Okay, number 4, the derivative of the natural log of x is 1 over x. Number 5, chain rule, we want to rewrite. So we have 2 times the sine of x. The 2 becomes a 1, so I'm not going to write it, times the derivative of sine, which is cosine x. Okay, the last one is actually from your 2.10 notes. It is a formula, so hopefully you looked back at your notes to do this one. And it is 1 over the absolute value of x, radical x squared minus 1. And again, you would have a note card with that formula on it for any tests or quizzes that you might have. All right, so today we're doing related rates day 2. We're going to start with example number 4. It says a particle P moves clockwise at a constant rate along a circle of radius 10 meters centered at the origin. The particle's initial position is 0, 10 on the y-axis, and its final destination is the point 10, 0 on the x-axis. Once the particle is in motion, the tangent line at P intersects the x-axis at a point Q, which moves over time. If it takes the particle 30 seconds to travel from start to finish, how fast is the point Q moving along the x-axis when it is 20 meters from the center of the circle? All right, so let's start by drawing a picture. We're going to start right from the very beginning. It says that we have this circle where this point starts at 0, 10 and ends at 10, 0. This is the circle with radius 10. Okay, so this particle is moving this way, and I'll put it right here, P. So as it moves, it has a tangent line. And the tangent line goes through P, tangent to the circle, and it hits the x-axis at some point Q. Q is going to change because as P goes from the top down to 10, 0, that tangent line also changes and moves. And what's happening is Q is actually getting closer to 0, 0 over time. Okay, so we're going to call Q x0. It's on the x-axis. It's changing, so x is a variable. And the thing that's really going to be key for us on this problem is that this tangent line, the blue one that I drew, is always going to be perpendicular to the radius. And the radius is always 10. Okay, that's just a fact of tangent lines. The tangent line is always going to be perpendicular to that radius that's on that circle there. Okay, so let's go through the parts in the problem and see what we can pick out. So it says that it takes the particle 30 seconds to travel from start to finish. Okay, so we're going to start with that. This is our theta right here, and theta is changing over time, okay? As P moves, this angle is decreasing. So the fact that it takes this particle 30 seconds to go from 0, 10 to 10, 0 is actually our rate of change for theta. It's the change in theta over time. Okay, and to go from 0, 10 to 10, 0, that's pi over 2. So it takes 30 seconds or half a minute for this to go from pi over 2 down to 0. Okay, this means that for 1 whole minute, it's going to travel pi radians per minute. Since theta, as this goes, is decreasing, we want our pi to be negative. Okay, and you can write yourself a note here. Theta is decreasing. I can't quite fit it. Okay, so let's take a look at this. The key here is that we have that right angle forming between P and the radius. Because of that right angle, we can use our Pythagorean, our trigonometric identities here. So we're going to use cosine because we have this side right here, the 10, and then we have this side right here, the x. So look at your theta, that is the adjacent side being the 10 and the hypotenuse being the x because of where the right angle is. All right, and it says, how fast is the point moving along the x-axis? That means we're trying to find dx dt because as q changes, x is changing. And then here it says when it is 20 meters from the center of the circle. So that's the particular x value that they want us to use at the end to solve this out. All right, so we're going to do cosine of theta is equal to, we have adjacent over hypotenuse. So my adjacent is 10, my hypotenuse is x. I'm going to rewrite it as 10x to the negative 1. And now I'm going to do my derivative. All right, so here we have derivative of cosine, negative sine d theta dt. And here we have negative 10x to the negative 2 dx dt. All right, so at this point, remember, we're looking for dx dt. Okay, that's what we're trying to find. What that means is we want to have something to plug in for every single other value that we have. So for instance, d theta dt, okay, we know that's negative pi. X, we know that's 20. The only thing that we don't know is theta, but we do know that we want this at the moment that x is 20, so that actually allows us to find our theta. So let's go over here. Cosine theta equals 10 over x. We want this to be the moment when x is 20. So that actually allows us to find our theta, which would be, by your t-chart, pi over 3. All right, so we're going to plug everything in now. So we have negative sine of pi over 3, d theta dt, which is negative pi. We have negative 10 times 20 to the negative 2 dx dt. All right, so this would give me negative radical 3 over 2. Again, that's off of your t-chart. And here it's negative 10, 20 to the negative 2. 20 to the negative 2 is 1 over 400, okay, because you're squaring the 20, you're putting it on the bottom. So it's actually negative 10 over 400, which is negative 1 over 40. Okay, we're going to times both sides by negative 40. So this gives me negative times a negative times a negative is a negative 40 radical 3 over 2 pi. And then that gives me negative 20 radical 3 pi. Okay, if I put that into my calculator or even on your phone, you can do that if you turn your phone sideways. Negative 20 times radical 3 times pi. It gives me negative 109 meters per minute. that is how fast our point Q is traveling along the x-axis. All right, I'm gonna go ahead and erase this, and we will look at number 5. All right, there we go. Learned how to pause it. You don't have to watch me erase everything anymore. Okay, let's look at number 5. A jet airliner is flying at a constant altitude of 12,000 feet above sea level as it approaches a Pacific island. The aircraft comes within the direct line of sight of a radar station located on the island, and the radar indicates the initial angle between sea level and its line of sight to the aircraft is 30 degrees. How fast in miles per hour is the aircraft approaching the island when first detected by the radar instrument if it is turning upward counterclockwise at the rate of 2/3 of a degree per second in order to keep the aircraft within its direct line of sight? All right, so we're going to draw a picture first. We have an airplane. We have some point here on this island. This airplane is traveling this way. All right, so this one is a little bit tricky because you can see here it says in miles per hour, and no other thing that they gave us in this whole problem is in the correct unit. So we need to kind of convert everything, okay? So we're gonna start with the 12,000 feet. 12,000 feet divided by 5,280 gives me 25/11 miles. If you did it on your calculator or on your phone and you got a decimal, the decimal is fine. Okay, but I'm just gonna leave it as 25/11. This is the altitude of the plane, so I'm gonna label it right here, 25/11. Okay, the next thing is that the initial angle of the aircraft is 30 degrees. You really need radians or it won't work out correctly. So this is actually going to be our theta that we want, 30 degrees, but we do want to make it into radians, so that would be pi/6. I did know that, but if you are not sure, you can always just think, how many times does 30 go into 180? It goes in 6 times, so pi/6 is the radians for that. Okay, this is our theta right here. And remember, we're not going to plug in the pi/6 until the end, okay, because it's the exact moment that they want us to evaluate. But the rest of the whole problem, we're leaving it as theta because theta is changing this whole time as this airplane moves. The angle is changing for this radar station to look at the airplane, okay? So that's like the main thing is whenever they give you these values, make sure that you're not plugging them in until the end, okay? All right, the last thing is they gave us this 2/3 of a degree per second, okay? So that is actually gonna be our d theta dt, because that's how much the theta is changing. Man, I do not have enough room here. Okay, I'm gonna go somewhere else, hang on. Okay. All right, so this is our d theta dt. 2/3. Okay, so we have a couple problems here. Number one, it's in degrees. Number two, it's in seconds. So we want it in radians and we want it in hours. Okay, so we're gonna start by changing the degrees to radians. In order to do that, we times it by pi/180. The pi kind of makes it into radians. The 180 dividing by the 180 kind of gets rid of the degrees. We then want to turn seconds into hours. So we need times by 60 to make it a minute, and then another 60 to make it an hour. Okay, so this gives me 40/3 pi radians per hour. All right. Okay, so we are trying to find out the speed of the airplane. So in order to figure that out, we're seeing basically how fast this bottom right here is changing. because that's how far away the airplane is. So however fast that's changing is the speed of the airplane. So we're going to call this x, and we are trying to find dx dt. Okay, and then looking at this triangle, it seems pretty obvious here that we're going to use tangent because we have the angle, we have the opposite, and we have the adjacent sides. Okay, so we have tangent of theta equals opposite over adjacent, so 25 over 11 over x. All right, now, if I am thinking ahead right now, when I think about doing this derivative, I'm going to have this x on the bottom, so it's actually an x to the negative 1. So I'm going to get negative 1x to the negative 2 dx dt. The problem with that is I actually don't have an initial value for x, right? They gave me the theta, pi over 6, they did not give me the x. So if I am wise, since it is a singular x, if I were to do the derivative of just a singular x, it would just be dx dt. And that would be great because I wouldn't have an x value involved, okay? So what I'm going to do here is I'm going to cross multiply. So the tangent is over 1, okay? So this gives me x tan theta equals 25 over 11. I'm then going to divide by the tan theta, and I get 25 over 11 over tan theta. Okay, one more step is to bring the tangent up to the top. It becomes a cotangent. Okay. Now, could I have done this problem without doing that? Yes. What I would have had to do is plug in the pi over 6 and actually solve for my x, right? Get my x value. I think this is a little bit easier. If you don't think of this, it's okay. You can still do the problem. Okay, so I know some of you are probably going, I never would have thought to do that. That's okay. I'm just looking at this thinking, look at now I have no issues. When I do that derivative of the x, it's dx d theta or dx dt, and I'm good to go. All right, so we're going to go ahead and do our derivative. All right, so I get on the left dx dt. On the right, derivative of cotangent is negative cosecant squared. So this gives me negative 25/11 cosecant squared d theta dt. All right, I'm going to plug everything in. I am not having any luck scrolling this down, so I'm going to erase my top part so I can keep working. So make sure you have all of this. Okay, so I'm going up here. All right, so we have dx dt equals, I'm going to plug everything in. So I have negative 25/11 cosecant squared of pi over 6 times d theta dt, which I found was 40/3 pi. Okay, cosecant is the reciprocal of sine. Okay, so sine of pi over 6 is 1/2. So cosecant, did I say cosecant before? That's what I meant. Cosecant is going to be 2 because it is the reciprocal of sine. All right, so this gives me, when I plug it into my calculator, it gives me negative 380.799. So I'm going to say this is about 380 miles per hour. Notice it's negative because the plane is going towards the radar station, so the distance between them is getting smaller and x is shrinking. So that's why it's a negative velocity.